The previous video gives you a decent idea of the difference between a scalar and a vector. A scalar being a value that does not have a distance, and a vector being a value that does have a direction, So I'm just going to go into a little bit more detail on the difference between distance, position, and displacement specifically. And we're going to start with distance. So I've drawn here a 100-meter track, and we're going to say that there's someone running from the start to the bottom, and they take a run all the way up to the top of the track. So what's the distance run at this point? Well, it's a 100-meter track, and they've run it once. So at this point, the distance, which we use d to represent, is equal to 100 meters. Now we can do a second example here, and assume this time it's made that same run, but then the person had to also stop and turn around and come back. So now it's run the length of the track 2 times. So what we have now is a total distance of 100 meters plus 100 meters, which means that the distance traveled is 200 meters. We're using a similar diagram here. The same track, only this time we're going to talk about position, which is a vector, and you can see that we still use d to represent the position, but it has a vector symbol over it. So it's this little arrow looking thing, and specifically an arrow that only has the head on one side of it, kind of like that. So I've given you 4 spots here, plus the origin. The origin, we use d, what we call d naught. So d naught is 0 meters, because that's our origin point. And we'll just write the positions at various other points. So if on that initial travel down the track the first time, d1, that position there, it looks like it's about half. So we'll say it's 50 meters. And we'll define the direction here to be forward. Alright, so in this diagram, this way is forward. It's always good to define it right on your diagram. So that means that position 2 is 100 meters, because we're now at the end of the track, and this is still forward. And now we have, let's do D3. So they've gone all the way to the end and come back. And this is, again, the same as D1. This is 50 meters forward, because this position is always done relative to the origin. So since the origin is defined down at the bottom, we are at 50 meters forward. And now D4, we are at 0. We're back to the origin. So it's 0 meters away from the origin. So you can see the difference here compared to when we did distance. D4 on the previous slide would have been 200 meters, and here it is 0 meters, because position is always relative to the origin. So always relative to the origin. Okay, we've got the same example here again, and this time we're going to discuss displacement. Displacement is in some ways similar to position, because we have the vector quantity on this still, so we're still going to be using the arrows, but most often displacement has a delta symbol in front of it. So you'll see delta D, so that means change in position. Okay, the triangle is change in, and then we know that the D as a vector is position. So what we have here is change in position. So that means if I want to find delta D, I have to know which points I'm finding the displacement for. So for instance, maybe I want to know the position or the displacement between D3 and D1. So the change in position going from the first to the third position So that really means I'm finding D3 minus D1. So we're looking for this subtraction here, which we know from the previous slide that D3 is 50 meters forward. And so is D1. I'm just going to put an F here to save myself writing forward a bunch of times. And so now we're subtracting vectors, right? So our vector forward goes this way, and our vector going forward again, so D, this here, you can represent D3, and this one represents D1, right? They both go in the same direction, but we're subtracting them. So you basically flip the second one. So D1 becomes this flipped vector this way. And then we're going to add them together. So you get D3 plus negative D1. Right? We're adding them together. This right now is not addition. I'm just showing you how the vectors are flipping. When you add them, you put them tail to head. So here we have D3. And we're adding it to D1, so it has to start where D3 ended, which means it goes like this. Okay, so what is here is 50 meters forward plus, and we flipped this one around, 50 meters backward, and they're opposites and the same value, so the answer is 0. And this diagram should reflect that. You can see here that where I started is where I'm ending, so the answer should be 0. So you can do this for any displacement. You can do it between D4 and 2. So let's go, we want the change in position between D2 and D4. So that's D4 minus D2. D4, if you look back on the other page, is 0 meters. D2 is 100 meters forward, and this is the same as adding the reverse, so plus 100 meters backwards, and what we get is 100 meters backwards as our answer, which should make sense to us because we're looking for the change going from D2 to D4, and that was going back towards the start, which is the opposite of forwards.